Thank you very much. So my name is McCrory, and I'm from the National Physical Laboratory in the UK. So today I'm going to be presenting some work on cluster metric sensitivity to irrelevant variables. So clustering algorithms are an important unsupervised learning technique, and they're used extensively for data analysis in data exploration. So data sets are constantly increasing in terms of complexity and dimensionality, and with this there can be a lot of irrelevant features which could impact the solution to a clustering algorithm. And normally you'd need to perform different clustering tasks on the data or subsets of the data, but this could still contain these irrelevant features. So in supervised machine learning, feature selection is quite well established. But for unsupervised learning, this isn't the case, and there's no clear objective function to be optimized. So if we can understand how clustering metrics are sensitive to irrelevant variables, then we could use some of these clustering metrics as a method for feature selection for unsupervised learning. So onto clustering algorithms. So clustering algorithms effectively group data into similar groups or clusters based on attributes inside of the data set. There exists lots of different types of clustering algorithms which work in different ways but effectively want to produce the same thing, these clusters which are all related within a cluster. But of all of the clustering algorithms that exist, k-means is still the most popular. So why is k-means the most popular algorithm? It's quite an easy algorithm to understand. It's easy and quick to implement, which is useful because you normally need to run k-means multiple times in order to get a good solution, because it works with random initialized centroids. You choose the number of clusters that you want the algorithm to find, and then it spits out randomly these k cluster centroids, and then it finds in the data set the points that are closest to each cluster, and this forms the cluster for each centroid. Then it computes the mean and then readjusts until the centers of each cluster is found. But k-means can be sensitive to feature scaling and outliers. So once you have your clustering solution, how can you assess how well the clustering algorithm has performed? And we can use these things called clustering metrics. So there are two main types of clustering metrics, either ones that compare to a ground truth or ones that use inherent features in the data set. So we've chosen 4 for our experiments, and these two here use the ground truth. Now, ground truth isn't always available in real-world data sets, but if you could find the next best thing by performing a clustering algorithm on a data set multiple times and finding the converged solution. So adjusted rand index has a range from 0 to 1, where 1 is the optimal score, and this is found by computing the rand index, which is the sum of the true positives and true negatives for an experiment, and it's divided by the expectation of the rand index. So here we're adjusting for chance, which is useful because k-means has a random initialization. Normalized mutual information works in a similar way, and this also has a range from 0 to 1, where 1 is the best score. But this works by computing the mutual information between your clustering algorithm solution and your ground truth. And then this is normalized by the entropy of your data, your clustering algorithm solution as well. So then the other kinds of clustering metrics are ones that use inherent features in the data set. So this could be things like distance. So here we chose silhouette coefficient. This has a range from -1 to 1, where 1 is the optimal score. And this compares each cluster individually and a specific point in each cluster, and finds the distance from this point to points within the cluster, and then points to the distance to points in another cluster. Silhouette can also be used to find the number of clusters for running k-means as well. And then Davis-Baldwin is another metric which works in a similar way. but this has the best score as 0 and no upper bound. But this now compares the distance within each cluster to the distance between each cluster, and it's divided by the number of clusters that you're finding. So we've used 4 different data sets, synthetic data sets, for our experiments. So these all have 1,024 instances and are comprised of 16 well-separated clusters, which are Gaussian clusters made up of 64 points. They're all equal sizes. And we have a range of dimensions from 32 dimensions or features to 256. And this data set also has the ground truth labels available, which means that we can use the ARI and NMI clustering metrics. So onto the irrelevant variables. So we've chosen to use 2 different distributions to generate our irrelevant variables. So a Gaussian distribution, which has a mean that can range from anywhere between the mean of the data set plus the standard deviation of the data set, and then a standard deviation which can range between plus or minus 2 of the standard deviation of the data set. And then the uniform distribution has a minimum of the mean of the data set plus 2 times the standard deviation, and a maximum of the mean plus 2 times the standard deviation of the data set. So here, mu and sigma are all respective to the certain data set that we're using. So it could be the one with 32 data sets that's computed differently each time. And then we have 3 different scaling methods. So for our data, we either leave it unscaled, so it's just our original data set with these new irrelevant variables added, or we center it by just subtracting the mean, or we standardize it by subtracting the mean and dividing by the standard deviation. Finally, I'll explain that we've measured how our clustering metrics, or the clustering algorithm performs by comparing the proportion of irrelevant variables to the true features in our data set. So this will make more sense in the upcoming slides, but if we have a ratio of 1 to 1, that means we have as many random variables or irrelevant features to the true features in the data set. So onto the kind of experimental procedure. So we've imported our data set without any irrelevant features, and then run the clustering algorithm on the data set, then computed the clustering metrics, and then we append a random variable, and we keep doing this kind of loop d times until we have d random variables appended to our data set. And then this whole thing is then repeated n times, so we can get a mean score for our clustering algorithm, and also we can see the standard deviation, the variance between the runs. So by doing it in this way, we get to a distribution of each metric as a function of the additional random variables. And this highlights the importance of the proportion of your random variables to your true features, so we can compare between different dimensions. So onto the results. So we've got 6 columns. On the first 3 all have the same distribution, the Gaussian distribution, and the final 3 have the uniform distribution. So I'll start by going through some of the findings for ARI and NMI, which are comparing to the ground truth labels. So for Gaussian, we see that neither of these are very sensitive to noise, even at a ratio of 3 to 1, so 3 times as many irrelevant variables to true features in the data set. These are still saying we've got a very good clustering solution. But it's very different when we have the uniform data and we see these kind of breaking points in each data set where the score goes very low, close to 0. And this is kind of separated by the different dimensions of each data set. So smaller dimensions have this breaking point sooner. Interestingly also, when we standardize the data, it then becomes very similar, the scores between the uniform and the Gaussian distribution. The silhouette coefficient is a lot more sensitive to additional random variables we see. Again, for the Gaussian case, then it's very similar trends here. And we see some kind of right shifting again between the dimensions here for the silhouette score in the uniform case. But these go away when we standardize the data. And similarly for Davis-Baldwin, we see a quick rise in the metric score showing that it's sensitive to these irrelevant variables. And there's some quite interesting dynamics going on for the uniform case with Davis-Baldwin as well. So now if we look at the standard deviation, so that last plot was looking at the mean metric score, now we're looking at the standard deviation. Again, looking at ARI and NMI, then we can see these peaks in the standard deviation. Now, interestingly, the peaks of these, the standard deviation score, this corresponds to the inflection point on these breaking points that we saw before. And we can see, yeah, again, they're partitioned like before. Standardizing also reduces the standard deviation we see. For the silhouette score, again, then standardizing really reduces the variance between the runs, and standardizing the data makes it the Gaussian and the uniform comparable. And then again, we did see some interesting dynamics for the Davis-Baldwin case, Davis-Baldwin metric score, and we see minor peaks here as well, which also represent the turning points in the results. So, in conclusion, we found that the mean scaling is equivalent to unscaling the data in all cases for all the noise and all the distributions. We found that standardizing reduces the variance considerably for the scores across all runs, and it makes the uniform noise and the Gaussian noise comparable, and also removes the tipping point for the Gaussian noise, the uniform noise. For the ARI and NMI score, we see that these are both quite similar scores and are not very sensitive to noise. And we also noticed those interesting tipping points for the uniform case. And finally, for the silhouette and Davis-Baldwin, these were highly sensitive to noise, especially from a noiseless baseline. And they quickly reduce in their score as we add the noise. So these could be potential candidates for feature selection for unsupervised machine learning. And that's everything. Thank you very much.